And you wanted to talk about other functional groups, other than which ones?
Okay, so basically, I would like to go through. Um, mm, mm, mm. I just want like a brief overview of the uh, other than the hydrocarbons.
Okay.
So basically, like the alcohols, ethers, amines. I guess I'm just not 100% sure like how in depth we need to understand all these different functional groups because I feel like I'm comfortable with the hydrocarbons. Uh,
The other functional groups, you do need to know some reactions, but mostly have to be able to identify them
okay.
in molecules. So the other functional groups, other than well, let's look at the hydrocarbons real quick.
Yeah.
The hydrocarbons are the alkanes,
Mm-hmm.
alkenes, alkyne, the cycloalkanes, and the aromatic. So hydrocarbon itself is not a functional group, but these 5 are. And what these 5 have in common is that you can have these with only carbon and hydrogen.
Okay.
Okay, additional functional groups are the haloalkanes, which means it's an alkane with the halogen. They're also called alkyl halides. And this basically means an alkane with a halogen.
Mm-hmm.
It's like calling someone, or like me, Tony Sartori or Sartori Tony.
Mm-hmm.
Okay, there's alcohol, amine, and ether. So you should know those 4 also. And so normally for a haloalkane, you write something like this. You need a carbon bonded to a hydrogen. For an alcohol, you need a carbon bonded to an OH. For an amine, you need a carbon bonded to a nitrogen. And for an ether, you need a carbon bonded to an oxygen, which is also bonded to a carbon. So a oxygen sandwiched between 2 carbons. Okay, then there are some functional groups that are called carbonyl functional groups. Now, this is not a functional group. The carbonyls are the aldehyde, the ketone, the carboxylic acid, the ester, and the amide. And a carbonyl is simply a carbon double bonded to an oxygen. That's all it is.
Right.
So an aldehyde has a carbon double bonded to an oxygen with a hydrogen bonded to that carbon. A ketone doesn't have any hydrogens bonded to that carbon, it has 2 carbons bonded to it. Carboxylic acid looks a lot like an alcohol, but you've got a carbonyl. So if you don't have a carbonyl, you have an alcohol. If you do have a carbonyl, you have a carboxylic acid.
Okay.
The ester, COC, looks a lot like an ether, but if you have a carbonyl, it's an ester. If you don't have a carbonyl, it's an ether.
Okay.
And the amide is the same thing as an amine, except for you have a carbonyl.
Mm-hmm.
So if you have the carbonyl here, it's an amide. If you don't have the carbonyl, it's an amine. So there are a couple of reactions you want to know for these functional groups. So let's go over those, okay?
Okay.
All right. So first of all, an amine is basic. So what that means is that it can accept a proton. So if you have an amine, and this is a very simple amine. So here's a carbon bonded to a nitrogen, and it looks like this. Okay. It can react with an acid like HCl. And what happens is these electrons make a bond to this hydrogen, and these electrons dump off onto chlorine. And you get the following. So notice that the hydrogen adds to the nitrogen. And when you take this H, you're basically taking an H plus because you're essentially taking the hydrogen with no electrons on it.
Okay.
Because these two electrons end up on chlorine, which becomes the chloride ion. So that's the amine. There's the carboxylic acid, which can donate a proton. So I'm actually going to show you acetic acid. And we're going to react it with methylamine. So these electrons will make a bond to this hydrogen, and these electrons will end up dumping themselves onto this oxygen, and you get this. So you'll see that the acetic acid has lost a proton, and because it has lost a proton, it's become negatively charged. The amine has picked up the proton and it's become positively charged. So this is an acid, and this is a base. So you should know those two reactions.
Okay. So this is just kind of something that we have to memorize, these reactions.
Yeah, but it's not too bad because here you can see both of them right here. In that basically the carboxylic acid loses this hydrogen,
Right.
and the nitrogen gets a hydrogen.
Mm-hmm.
So it doesn't have to be from a carboxylic acid. It can be from just a regular acid here. Likewise, this doesn't have to react with an amine. It can react with a base like the following. So we know that sodium hydroxide is a base, right? This is sodium hydroxide. It's a sodium ion and the hydroxide ion. And what will happen is this guy will make a bond to that hydrogen, and these electrons will dump off on oxygen. And here we get Na still, and then plus HOH. So here's an acid and a base, and you make a salt and water. This Na plus this is the salt. And salt
So,
is just a another word for organic or inorganic compound or ionic compound.
mhm. How do we know that amine is basic? We just know that because that's what they.
It's because of that lone pair on the nitrogen.
Oh, okay, okay.
So this guy right here can bond to an H plus. Okay.
Mhm.
And this H plus is usually going to come from an acid of some sort,
Okay.
like a carboxylic acid or HCl or H3PO4 or HNO3, something like that. And the carboxylic acid, so whatever is over here can do this. So if I take this hydrogen off with no electrons,
Mhm.
it becomes an H plus.
Mhm.
And those two electrons which stay on the oxygen make that a -1 formal charge.
Right.
And the reason this happens is because this guy is actually resonance stabilized. So these electrons which are stuck on this oxygen actually are shared between this carbon and this oxygen. So they're spread out amongst 3 atoms, not stuck on one, which makes it really stable. Oops, forgot that. And the way to think about that is as follows. I'll let you catch up here.
Can I see the previous page real quick?
This is similar to what we had just done.
Okay. Okay.
So what this guy is, if you look at it, these 3 atoms, this guy's going to be trigonal planar, right?
Mhm.
Okay, so if I kind of draw it that way, trigonal planar, but I'm going to draw it this way. So here's one carbon, here's one oxygen, here's one oxygen. Lone pair, 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 and whatever's over here. So we'll call this R. R for the remaining part of the molecule. Okay, so what is the hybridization of this carbon? It's sp2 hybridized. So that means that carbon has an sp2, an sp2, and an sp2. This oxygen, it turns out, is also sp2 hybridized. So here's a bond between that oxygen and that carbon. And let's see now. Here's an sp2 and here's an sp2, and these have lone pairs in them. This oxygen is also sp2. And these have lone pairs in them. But you'll notice we don't have the double bond here. So where's the double bond come in? Well, there's an unhybridized P here, an unhybridized P, and an unhybridized P there. So here you actually have a double bond with a pair of electrons in it, a pi bond. So this is the sigma bond, this is the pi bond, and here you got a pair of electrons. Well, what can happen in this particular system is that these electrons can move right here and make a bond. So what I'm going to do now is I'm just going to draw the carbon, the oxygen, and the oxygen, and I'm going to focus just on the pi bonds, okay? Or the p orbitals.
Mm-hmm.
So we have a pair of electrons here and 2 electrons here. What can happen is these electrons can form a bond like that, and these electrons will end up being over here. So we can get those electrons to kind of spread out over everything, and what's really happening is this. These 4 electrons are spread out amongst all 3 atoms, which makes it pretty stable because they're spread out. They're not congested into a spot stuck between 2 atoms. They're spread out.
Yeah.
Okay, so that's why this thing is really stable. And that's why this thing is okay with losing a proton. It's because what it makes is stabilized by resonance.
Mm-hmm.
Okay, now the other reactions you need to know, you need to know polymerization reactions. So alkenes can polymerize, and they make something called an addition polymer. And here's what happens if you have an alkene. So the example I'm going to give you is how you make polyvinyl chloride. Have you ever heard of that?
Mm-mm.
The acronym is PVC.
Oh, yeah.
So I'm going to show you how to make polyvinyl chloride. This is called vinyl chloride right here. Okay, so what happens is you initiate the reaction, and I'm going to show you one vinyl chloride, another vinyl chloride. And you can see I'm not trying to draw these in 3 dimensions like they are with the molecular geometry, because each of these are trigonal planar. But what happens is you have an initiator with 1 electron come in and try to bond to that carbon. But you need 2 electrons to make a bond, so one of the electrons from the pi bond comes and helps this guy make a bond. So what's going to happen is your initiator will bond to that carbon. But here you still have 1 electron left over. And what happens with that is it makes a bond to this carbon. But that 1 electron needs another bond or another electron, so it comes from here. And so what happens here is you then make a bond to this carbon. Now here you have 2 electrons, and one is going to go out and kind of attack this carbon, and 1 electron from this bond will make a bond. And it just goes on and on and on and on as long as you have the monomers. So this just continues on and on and on as long as you have these pieces to put together. Now, when you see this, can you see how this piece here is the same as this piece here?
Yeah.
And that's the same as this piece here?
Mm-hmm.
So this is how you write the addition reaction with alkenes. So here we're looking at a polymerization. with alkenes. So we start off with this. So this is a very generalized alkene. So here's your alkene, and we have N of these. So when you polymerize them, to draw the polymer, let's take a look back here. Do you see that this piece and this piece and this piece, they all look just like this,
Yeah.
except no double bond.
Mm-hmm.
And then those pieces connect together. So what we do to draw the polymer is we draw this again without the double bond. Okay, and this connects to a preceding monomer. This connects to a following monomer. And how many of these do we have repeating if you start off with N?
N.
N. So that's how easy it is to draw a polymerization reaction.
And what is the initiator? Like what is?
Well, you don't need to worry about that. You just need to do this. So what would the reaction be if this were your starting material? Try and draw the polymer. When you're done, give me a heads up and then I'll draw it for you and we'll compare the two, okay?
Okay. Well, it's just the same. You just remove the double bond, right, between the carbon and carbon.
Give it a shot. Don't talk through it. Just do it, and then we'll see. Are you done?
Yeah, I think I'm done.
Okay, well then it looks like this. So I've drawn that without the double bond. Then I draw lines to each of these carbons, parentheses and an N, and I'm done.
Mm-hmm.
Is that what you got?
Yeah.
Okay. Now, do you want to show me the polymer for Teflon? So Teflon starts off with this. Carbon-carbon double bond, of course. So what's the Teflon polymer look like? Give it a shot. And when you're done, let me know.
I'm done.
Because it's so darned easy, right?
Yeah.
And that's why I said, don't talk through it, just do it. Because once you start doing it and you see that you're right, you're like, oh, okay, I got it. Is that what you got?
Yeah.
Okay, so there's a bunch of different starting materials that are given in your book. And the beautiful thing is you don't need to know what any of those starting materials are. You just need to be able to put them together. Okay?
What do you mean by we don't need to know what the starting materials are?
Well, you don't need to know what, for instance, this starting material here is called styrene. And here, this is polystyrene.
Oh, like the PVC and.
Yeah, you don't need to know that this is styrene and this is polystyrene.
That's given to us.
Yeah. This one, you would, if I gave you the name, you would have to draw it. And this would be tetrafluoroethene. So how do you know there's 4 fluorines?
Tetra.
How do you know it's 2 carbons? F.
Ethene. Yeah.
F. How do you know there's a double bond between the carbons? Ene.
Mm-hmm.
That's it.
The ethene.
Yeah. So it's pretty easy. That's one polymerization. The other polymerization is based on condensation. So this is actually two reactions that we're going to look at: condensation, which is a type of polymerization. Well, it's going to be a type of polymerization, but what happens is you take a carboxylic acid plus an alcohol, and you get an ester plus water. Okay, so I'm going to take a very simple carboxylic acid, CH3, C double bond O, and OH. Now notice this OH, I'm writing the OH in red. And we're going to take this alcohol here. It's going to be ethanol. I'm going to write the H here and OCH2CH3. So this is ethanol and this is acetic acid. Now, the reason I've drawn these in red is because the red atoms combine. So what happens when you take OH and H and put them together?
Water?
You get H2O, right? 2 hydrogens, 1 oxygen. So what happens to these other pieces? Well, I'm going to take the left-hand side of my carboxylic acid here, and I'm going to attach it to the alcohol. And that is a condensation reaction between a carboxylic acid and an alcohol. And you should also know this reaction, that if you take an ester and add water to it, you can turn it back into an alcohol and a carboxylic acid. So this is really two reactions, but we consider it to be one. So let's try another carboxylic acid. Only this time, I'm not going to bother showing you the red atoms. I'm just going to draw it like this. So show me the products. And the reason I showed you these in red is because it's always the OH from the acid and the H from the alcohol. Always. We know that. It's well studied. So it's just a fact of life that I'm sharing with you. So see if you can figure out what goes on here. Is it a battle? Tell me when you're ready. Now, let me show you a way to help you with this. You should always do this. Why am I circling that?
The hydroxide? I don't know.
It's not a hydroxide.
I'm sorry.
It's not a hydroxide. It's an OH. Why am I circling that? Well, the same reason I would circle that. Why am I circling that up there? Where does it end up?
With a H, creating water?
Yes. So I'm going to circle that. Those things make H2O. So I'm going to look at this and I'm going to say the same thing. Here's the OH, but how am I going to make water? Where's the H come from?
Does it come from the HO?
Yes, just like above. You see, you're being fooled by this little extra line here, but that doesn't matter. So what does this HO and this H make?
H2O.
H2O. Now, how do we get the other product? Well, you take what's left over and attach it to what's left over.
Mm-hmm.
And that's it. Kind of got it?
Yeah. So if we're seeing OHs and Hs, then it's most likely gonna form water.
Well, no, as long as you have a carboxylic acid
Right.
and an alcohol,
Mm-hmm.
you'll
Then it
form
will
water.
form water. Okay.
Yeah, not just OHs, because this is essentially not going to do anything. I mean, you can get these to react, but it's really hard. So these are OHs, right?
Mm-hmm.
Why don't these condense together?
Because it's not a acid. It's not a
It's
carb.
not an acid. That's an alcohol, so that works, but that's not an acid.
Okay.
You need two to tango for this particular reaction,
Mm-hmm.
okay? And they have to be the right type of functional group.
So for condensation, there's always going to be an acid and an alcohol.
No, this is one type of condensation.
Mm.
So let's try it again. You didn't seem to show the proper enthusiasm to make me think that you got it. So I'm going to draw another acid. Do you see this acid here?
Yeah.
And it's just a line drawing, right? It reacts with this alcohol. And here it could go both ways. What are you going to get here? Now remember, I showed you a way to do this. Copy these molecules down and then circle the things that become water. And then put the other two pieces together and let me know when you're done.
And then.
Okay, so this and this become water.
Mm-hmm.
So that means I'm going to draw this piece without the OH. So there's no OH. And I'm going to connect it to this piece. And then I'm going to write H2O. If you want to, maybe it'll help you to write HOH so you can see the two pieces that add together.
Mm-hmm.
Did you get something that looked like this?
Yeah, I got the same thing.
Excellent. Now I'm going to try it again. Are you ready? Actually, we're going to make this we're not going to make that a chlorine. We're going to make it we'll leave it like that. So what are these going to do?
The same. You're gonna form water, and then.
Okay, so which one of these becomes part of water as far as the OH goes? The one on the left or the one on the right?
The HO on the right.
Correct, because it
Because
is
it has the
attached to the
carbox.
carbon double bond oxygen, which is called a carbonyl.
Yeah.
Okay, so these make water. And go ahead and continue drawing the product. And let me know when you're done.
I think I'm done.
Now, what I would do here is I would not bother trying to switch these around. I would just go ahead and draw that piece, the plus sign with the oxygen, and I'd connect it to this piece, which means the double bonded oxygen like that.
Oh, okay.
So I just take the pieces that are left over and shove them together. That's it.
Mm,
So I don't need to worry about which one's on the left and which one's on the right. I just care about what are the parts of each that become water. And after I've dealt with that, the leftovers get attached together. And I attach them together from where I removed the H and the OH. Are you with me there?
yeah.
Okay, so let's try this one. Actually, whoops, made a mistake. So this one's going to be tough for you. And let me draw it a little differently, okay?
Mhm.
Oh, we got off track. So this is kind of a fun one. Okay, so draw the product, or products, I should say.
Hmm.
Did you circle the parts that are going to become water?
Yeah, I think I mean, I made a guess.
Okay, so this is going to become water.
Yeah,
So what I'm going to do is I'm going to redraw this.
that all attached together.
That's right. And so now I have to attach this carbon here to that oxygen. So like that.
Yeah, that's what I did.
And that's it. Now let's try this. So do you see the house?
Hmm.
So here's the house with a little, I don't know, you could call that a chimney. And this could be one of those little holes you put in the ceiling for light to come in. I'm not sure what those things are called. Okay, when you add H2O to this, what are you going to make?
You're gonna make a carboxylic acid and
Okay, so draw it. So what bond do we have to break?
the one between the oxygen and the carbon.
Which oxygen, the one that's double bonded or the one that's single bonded?
The single bonded one.
Okay, so right here, is that right?
Mm, mm,
That's what you described between the carbon and the single bonded oxygen.
no, I think it's the other one.
You think it's this one here? Or do you think it's
Oh
this
no,
one
no,
here?
no. No, no, the other one. Yeah.
Nope, you had it right the first time. It's between the carbon and the single bonded oxygen.
Yeah, that's what I meant. That's what I meant.
So this is correct.
Yeah,
Okay, so
I decided I was correct the first time.
let's break that bond. So you see it now, I've broken it.
Mhm.
Now, what do I add to the carbonyl?
You will be adding the O and the H. The
That's right. And
OH,
what will I add to the oxygen?
the second H.
So is this a carboxylic acid and an alcohol that could be used to make water and this ester?
Mm-hmm.
Yep. So that's one condensation reaction. Are you ready for the next one?
Yeah.
So you can take a carboxylic acid again. So here's my carboxylic acid. And this time I'm going to add an amine. So this is an amine. Now, guess what I'm going to circle here? What am I going to circle?
The same. The OH.
And
The H.
what are they going to make?
Water, H2O.
And what do I do with these remaining pieces?
Attach them.
Attach them. And you get an amide. So do you see this is the same as the other reaction, only with an amine?
Mm-hmm.
But it's exactly the same in that you take an H and an OH and you make water and you attach the other two pieces together.
Mm-hmm.
Let's try another one. Now this time I'm really going to mess with you.
So this is not an alcohol though, right? So
No, it's an
an
amine.
alcohol?
This is an amine.
Oh, I guess I just thought it had to be an alcohol for it to be a
Nope.
condensation reaction.
Nope, there's two condensation reactions. One
Oh,
with
okay, that's right.
And one with an amine.
Oh, okay, right. Okay, got it.
Okay, so draw the product here. Now, can you see how I'm messing with you? Because there's the OH and there's the H, but they're not lined up correctly. What are you going to do? You got two choices. Figure it out or curl up into a fetal position and just kind of wait for the world to end.
Just like reflect it, rotate it.
Which one?
So just like, so for example, I mean, I guess you could do it with either one, but I would probably do it with the amine.
Okay, so that means you're going to draw this the same way.
Like draw a reflection of the amine.
Okay, so like, did you do it?
Yeah, so basically it's like a, well, I haven't, let me draw it.
Oh, yes. Now I drew it.
Draw, though.
And now you see the answer.
That's exactly what I was going to draw, just like a flipped version of it.
Okay. How hard is that?
But I was going to actually draw it like instead of the end, the line going down, just going straight. Like, so it's an exactly a reflection of what was drawn on the other side.
This is a reflection.
Yeah, I'm just talking about the line that goes from the carbon down to the end.
Oh, this guy?
Yeah, I was gonna draw it straight.
Oh, no. Like this. Maybe like that.
Yeah.
That doesn't look as cool. Because that's trigonal planar. That looks more trigonal planar.
Yeah, that's what I would have done, probably just draw a reflection.
Okay, are you ready for a condensation polymer? Are you ready? Imagine this is your alcohol. And this is your acid.
They're all carboxylic acids, right?
No, these are alcohols and these are carboxylic acids.
Right, but I'm saying all the condensation reactions require a carboxylic acid.
Yeah, the ones that we do in this class, yeah.
Okay.
Not all of them ever, but the ones we cover in this class. Now I'm going to draw this like this. And you'll notice what I'm doing is I am drawing this is called a diol, and this is a diacid. And I'm drawing the diol, diacid, diol, diacid, diol, and I've run out of room, so I'm going to stop. Okay, now I'm going to circle these two and this guy. What do those things make?
Water.
I'm going to circle these two and this guy. What do they make?
Water.
I'm going to circle this guy and these two. What do they make?
Water.
So do you see what's happening here? This guy is going to attach to that guy. So it's going to look like this.
It's going to be a chain.
Yes. And it's just going to keep going and going and going. For how long? For as many of these as you have. So let's see, what is the repeating unit? The repeating unit. Can you see that that is one unit?
Mm-hmm.
And this is another of the same?
Yeah.
So the way to draw this reaction, it can be done one of two ways. You see the alcohol?
Mm-hmm.
Draw it without the H's because they're going to be taken off. What are you? How are you going to draw the acid in the product?
Without the OH.
That's right. You got it. And then parentheses and an N, and there's your answer. Now for this one, you could do it another way. You could say, well, I'm going to start with the acid instead. And then I'm going to draw the alcohol without its H's. These two answers are the same.
So it's two H's being removed and two OH's.
That's right. And so, of course, we're just going to put H2O over here and not worry about how many.
And in terms of knowing like that we're supposed to remove both of the H's and both of the OH's, is it just because we see that there's like a combination of H's and OH's on either side and we're just supposed to know like
The
there's
key
two
is
OH's
this.
here, two H's there.
The key is
Oh, it's the in the name. Okay.
Well, you can look and see it's a diol and a diacid.
Right.
That's the key.
Because it's two, yeah.
Yeah.
Okay.
So let's see if you can draw a polymer for me. So draw the polymer you're going to form here. You've got N of these and N of those.
Yeah. Okay. Hmm. Okay, so I removed the
Well,
H's.
yep. Do you have it drawn?
Yeah, I already drew it.
Okay, so I'm going to show you my answer.
Oh, I forgot to put that extra bond out. Yeah.
Okay, so I got rid of the OH from here, and that's it. You could draw this other ways too, like this. I'm drawing this up at an angle because this guy's coming down.
What about the plus H2O?
Oh, yeah. Okay, now let me give you another one.
But you don't have to write how many H2Os, right?
No, don't worry about that. Okay, draw the product from these two. Tell me when you're done.
Sorry, I got confused for a minute.
Yeah, that's because I put the acid first and the alcohol second.
Yeah, but I think I'm good.
What do you take off of the acid?
The OH on both ends.
The OH on both ends. And
Then
what do
the
you
hanging
add?
bond.
What do you add where those OHs were?
A hanging bond.
A bond. What do you take off of the alcohol?
Just the H
And what do you
on both sides.
And what do you put there instead? A bond, right?
Right. You attach the O to the carbon and then leave a hanging bond
So there it is.
in the last O. Mm-hmm.
Do you know what this molecule is called? Because that is an ester, right?
Mm-hmm.
And if we take a look here, can you see that this is an ester? C double bond O, OC.
Mm-hmm.
Can you see this is an ester? C double bond O, OC.
Yeah.
Can you see this is an ester?
Mm-hmm.
So it's not one ester, it's a lot of them. So when you have a lot of esters, it's not a monoester, it's a polyester. The greatest invention ever hoisted upon mankind.
Oh, right. Yeah, polyester.
Polyester.
I was like, yeah, polyester.
I bet you're
I
wearing
didn't make
polyester right now.
Probably like mix cotton.
Are you wearing any sort of a t-shirt made out of say,
cotton?
Yeah, it's probably not pure cotton. There's some polyester in there.
Yeah, there's polyester in everything.
Yeah, and especially pants these days, you know how they kind of make them stretchy?
Hmm.
Cotton doesn't do that. Polyester does. So no doubt you have some polyester right now. And polyesters are really wonderful because when you make these things from the monomers, you can add in dye molecules and they kind of get trapped.
Hmm.
And so you can get these really beautifully colored threads, which you can then use to make really bright and vibrant colored clothes.
What is it made out of?
What is what made out of?
Polyester.
Polyester? Polyesters are
Yeah.
made out of different carboxylic acids and different alcohols, depending on what you want in your polyester.
Hmm.
So they're just made out of different combinations, whatever
So it's like
works.
completely synthetic.
It's completely synthetic. And just think about all those brightly colored shirts that people wear. Wouldn't be possible without polyester.
Hmm. It's just hard to
So
make that connection of like something that's completely synthetic
it is. So
or doesn't have like a organic, like something from that it was made out of.
it's made out of oil essentially. So think of a disco. You ever seen those old movies with disco dancing and stuff?
Yeah.
And they're wearing those really bright blue, red, yellow colored shirts and stuff. You wouldn't have that without polyester. They'd be wearing dull colored shirts and it wouldn't be disco. It'd be like, I don't know what you'd call it.
A
You call it,
hippie thing.
you call it,
It'd be
yeah,
earthy colors.
with all the neutral colors. But even hippies appreciate the multicolors, right? Because they make tie dyes,
Yeah.
but they're natural.
Yeah.
Of course, the dyes they use aren't natural, but
Yeah. I don't think you can achieve those colors with natural dyes.
okay. And you can take that from the hippie shit. Okay. Now I'm going to show you another polymer. So this is not a dye alcohol. What is it?
Mm.
Nitrogen bonded to carbon. What is that?
Mm.
It's an amine.
Oh.
You remember our other condensation can be between an amine and a carboxylic acid?
Yeah. So it's either an ester or an amine.
An amide. It makes an
Amide.
amide. So here,
Amide,
guess what
yeah.
we're going to do? We're going to take these hydrogens off, these OHs off, and we're going to stick these together. And you also get H2O. So have you ever heard of nylon?
Mm-hmm.
There's many different types of nylon, but the nylon that you find in like stockings is called 6,6 nylon. And the way you make it is you start off with the following. Okay, count with me. This bonds to the nitrogen, this bonds to the nitrogen. 1, 2, 3, 4, 5, 6. 6 carbons, all right?
Mm-hmm.
Now the acid looks like this. count with me. 1, 2, 3, 4, 5, 6.
Hmm.
So why is it called 6,6 nylon? Because there's 6 carbons in the amine and there's 6 carbons in the acid. So if you start off with N of those and N of those, what are you going to make?
N of those?
Yep, N of this and N of that.
Hmm. I'm not sure. What was your question? How many? Like N of it? Or what is it gonna
Oh,
make?
what are you going to make? This is the model. Yeah,
Okay.
so draw the polyamide. Basically, you're drawing the polyamide for making nylon,
Okay.
because you never know when you're going to be stuck in some sort of situation where you're going to have this amine, this diamine, and this diacid, and you're going to have to build yourself a rope, and you're like, oh, I know how to do this, and you mix the two together, and then you start pulling rope out of it, and you go, I can escape.
I mean, I don't even know what kind of form this is in. Like,
Well, it's just like the one above. What do we take off of the amine?
oh no, I'm just wondering, like, no, on your analogy, I'm like, I don't even know how you like, are these liquids, gases? Like, I don't really
These are
understand. Like,
liquids. These are
oh,
liquids.
okay.
You pull solid out of them.
Oh, okay. That's why I was like, I never like, I feel like it's hard for me to conceptualize like how you actually make something out of these.
I'll show you a video in just a moment.
So, okay, so yeah, just remove the H's from,
So when you're done drawing the product, let me know.
okay.
And I'm going to look up a video on 6,6 nylon. This is something I usually demonstrate in class. Okay, when you're done, let me know.
Yep, I'm done.
Okay, so I'm going to take the NH and I'm going to make 1, 2, 3 mountains. 1, 2, 3 mountains plus a half a mountain. And I'm going to go to N and I'm going to keep that H and I'm going to draw a line like that. And I'm going to connect it to this guy. So that means I'm going to go ahead and connect it to that double bonded oxygen and take that OH off and that OH off. I'm going to go down, up, down, up, down. And that's basically it.
Mm-hmm.
Plus what?
H2O.
There you go. Okay, so I'm going to do a new share with you. I've never watched this video before, so hopefully it's good. And they're going to show us how to make 6,6 nylon.
Okay.
Dig the music.
Very funky. This is more of like an organic chemistry lab, something you do in organic chemistry.
What's that?
This is something you do in organic chemistry.
If you're lucky, you get to.
Okay, so it's like pretty advanced stuff.
Yeah. Okay, do you see this liquid, how it looks like there's nothing in it? That liquid we just saw has the diamine in it.
Right.
And this liquid has the diacid in it. And the pieces are so small that you can't see the individual pieces. So there's tiny little molecules in each of those liquids. Now they're pouring one into the other. And in this reaction, instead of making water, you actually get acid. But nonetheless, we're not going to worry about that. This is a polymer reaction. So they take some tweezers in there, and that's a solid. And watch what they do. They're twirling the rod, and more and more and more and more of the solid is being pulled up. So when do they stop making that solid? And the answer is when they run out of reactants. Now, what I do in my demonstration is instead of twirling it like that, I take the rod and I lift it from the tabletop to above my head. And then I'll take the beaker and put it on the ground and lift that up to my head. So you have a piece of string that's 6 feet long.
That's a lot that can be made from such a small amount.
Yeah.
Good.
And this is a synthetic thread. And you know what nylon's good for, right? For when you rob banks, you put the stuff over your head. Actually, I don't know if it's good for robbing banks because I've never done that. I always felt like banks robbed me. Okay, so that's 6/6 nylon. So now hopefully you've got kind of the idea that you're taking these small little molecules and you're putting them into a really long string that you can actually see. Pretty amazing, right?
Mm-hmm.
Now,
Like
why
magic.
Why are polymers so important? Well, it turns out that all organisms are made out of polymers, or we use polymers. The two most important polymers that we use are, well, not the two most important, but two very important ones are proteins. Proteins are polymers, and they're polyamides.
Mm-hmm.
Another important polymer that we use is something called DNA. And DNA is not a polymer like we've seen. It's actually called a phosphate polymer, where you're using this guy here, kind of like a carboxylic acid. So can you see that this is basically going to be the OH and the OH of the polymer?
Mm-hmm.
And then you add it to something else, an alcohol. Like maybe the alcohol you add it to looks like this. So this adds to that. And the way you would draw this sucker out would be this way. So do you see I've taken the OHs off of that?
Mm-hmm.
What am I going to take off of this guy?
Just the H.
The H. So here's the H. And I got to draw my house. And then I got to take the H off of there and boom. So this is a phosphate ester. And actually it's called a triphosphate ester because there's 3 of these.
Mm-hmm.
Now, what you actually find in DNA is this. I can't remember exactly, but it is a 5-membered ring. And I think it's like this. I'm going to do that. So you find that in DNA. So do you see how this is similar to what we've been talking about?
Yeah.
Because don't these look like carboxylic acids except for their phosphorus?
Mm-hmm.
So polymers are hugely important. And in proteins, what happens is that you actually have this. Uh, so to draw a polymer of this, you would take this guy off and that guy off. N times. So see here in this case, you don't have a diamine or a diacid or a diol. You've got one side that's an amine, the other side that's an acid, and this can combine with the amine of another one. So do you see how these can make water?
Mm-hmm.
So that's what happens in proteins. And in proteins, it's even more fantastic because you don't have to have polymers that are repeating units. You can have different Rs, which makes them really specialized.
Mm-hmm.
But this is a polyamide. But because it is special, we call it a polypeptide, where the bond that forms here is a peptide bond. You ever heard of polypeptides?
Yeah.
Polypeptides are just polyamides, but very special. Okay, so that kind of is all of the reactions you need to know. Okay.
Yeah, that was very helpful. I think I just need to kind of like, have you gone through all the Q&As already in the other sections? I mean, in the other Q&As? Have you gone through all the questions at the back of the chapter in the other Q&As?
I've gone through most of them, not all of them. There's some others that I want to cover.
Okay.
It
Are you
looks
gonna
like
do them tomorrow in the AM? Or
yeah, I think there's I want to say I have like 12 more problems that I want to go through.
okay.
But also other people have been asking questions too. And I also posted a video answer key to the problems in chapter 23 to the homework.
Oh, okay, to the homework. Okay, perfect.
Yeah, there's a video answer key.
Yeah, I think it's just, I don't know, chapter 23 is very challenging. And I think just getting started, it's hard for me to read the chapter.
Well, you should never read the chapter. You should just start doing problems.
Yeah, I want to go through the Q&As and like catch up with those. I've been like really caught up.
So there are some Q&As where people have asked about isomers. There's other Q&As where people have asked about problems in the back of the book that I haven't assigned. There's some other questions where people were asking about reactions also. But a lot of the problems I'm doing in the back of the book that people ask about are reactions.
Okay. Have you been getting a lot of calls in the morning? Is that
I usually get a regular, do you know Charlotte?
Yeah, Charlotte.
Charlotte usually calls in the morning. And
yeah.
However, she said she can't call in, I think, Thursday or Friday because she's working or something like that.
Okay.
Usually around noon, or I should say at 1:15, usually I get no one. And then,
you have a morning person, a
yeah,
PM person, and an evening.
yeah. This morning I had Rebecca. Do you know Rebecca? You know Rebecca, right?
Yeah, Tony, I've been here on calls with Rebecca.
That's what I thought. It's hard for me to remember who
And I
was
also
there.
watched the Q&A, so I I know Charlotte and
Rebecca, and that's about it. And yourself.
and you said Noah. Um, yeah, but yeah, this is a very challenging chapter, and I think I just need to like spend the whole evening going through the Q&As.
Yeah. Oh, yeah. And there are the Q and A's with no one where I'm just talking to myself. That's a really interesting conversation.
Yeah, so I do want to try to make it tomorrow in the morning. I think the AM might be a good idea.
Okay. Yeah, you can always be a fly on the wall for Charlotte's questions.
Yeah, that works for me because I feel like I don't know, I just haven't like been able to like really wrap my head around chapter 23, and I haven't done like the amount of work and effort required to try to wrap my
Right.
head around it.
But on the other hand, I'm going to tell you, I think you get a lot more out of it when you're not a fly on the wall, but you're being challenged by me to think about it.
Yeah, I think that's my hard part with watching the lectures is that I get really passive and I'm just like watching it and
Yeah.
like my brain doesn't work that way. It's like really ADD. I have like a really like ADD brain. So if I'm like,
So what you may try when you're watching those lectures or whatever, or when you're watching me do example problems, if it's a problem where you've seen something similar before, just put pause and come up with your own answer and then put play and see if they match.
yeah, I need to try to interact more with the videos because I feel like that's why I'm like, I know I need to make it to the lectures because they're the things that help me the most.
And there are even times when you're watching the lectures when I'm going to say, okay, so come up with the answer, push pause. And then I
Yeah.
say, oh, welcome back.
Yeah, I just need to be more conscious about not being a passive learner because I could easily watch something and or just listen and just feel like I completely zoned out because I'm
Yeah.
not like actively engaging with the material.
Yeah. I have had students tell me that on the first exam they did very poorly, and I asked them how they prepare, and they said, well, I read the material until I understood it. And then my
Yeah.
question was, well, how do you know you understood it? Well, because I read it. You don't know
Yeah.
you understand something in chemistry until you try to do it. If you can do it, you understood it. If you can't do it, you didn't understand it. It's pretty cut and dried. It's the same with most science classes.
Yeah. I think the people that do the best are the ones that are actually going through the questions and at the back of the chapter
Yeah.
and the homework
And
questions.
writing out answers, not thinking about the answer and saying, oh, yeah, I got this, because you don't. You don't got this. It's kind of like rock climbing. You look up the side of the cliff and you go, yeah, I got this. And then halfway up, you realize, oh my God, I'm going to die.
Yeah. Sometimes it feels like
I
that.
don't got this. I wish I was belted in. Luckily, that
Yeah.
hasn't happened to me.
Yeah. Yeah.
Well, I mean, the dying part. But I have gotten halfway up and said, oh my God, I'm going to die.
Yeah.
And then
I
somehow
know.
or other, I managed to make it.
Yeah, I used to do rock climbing too,
Yeah, it
but
sounds like it.
not really challenging like what you and Rebecca were talking about.
Well, that's her, not me.
Uh,
I've done the toughest thing I've ever done was probably a 5.6. That's it. And I was not
yeah,
a lead or anything. I was I followed.
I'm just all about safety first, so it's kind of hard to like wrap my head around being in such a.
Yeah, and that's why it's good that I stopped, because I was not about safety first.
Yeah, I'm totally fine with rock climbing as long as I'm attached to
Well,
a
yeah, top rope or something.
to a rope.
A rope going up through a little bolt at the top of the thing that is secure.
And I'm fine with bouldering as long as it's like 5 or 6, 7 feet from the ground.
Yeah, exactly. That's the kind of guy I should have been, a boulderer, because I never liked the rope part. But you have to boulder at the right place, or you have to have the right frame of mind. What I mean by that is you can't boulder on a cliff that's 100 feet tall and have the frame of mind that you just want to go up. You got to go across. You know what I
Yeah, I
mean?
stick to rock climbing gyms. I'm okay with that.
Well, those are no fun because the holds are just these big monster things that anyone can hold on to.
That's not true. Depending on like yeah, it just depends on like they get more challenging like the more they
Okay, I agree. They start you off nice with big holds. But what I also hate is for the real expert ones, they give you these things where the hold is the size of an eraser. And you're like, really? I'm supposed to hold on to this with my finger and my thumb? Who are you?
yeah, it's really hard. Some of those
Yeah.
get really challenging.
Yeah. And then it also doesn't help if you're not flexible, like I am not flexible, and you're massive. It's hard to hold
Yeah.
a lot of mass. I
All the
wish I
people
was
you
skinny.
see that are the best rock climbers are like super lean and just like
Super
really
lean,
flexible,
super flexible, and they
have
tend to
some
be
upper body
long.
strength.
Short people aren't always the best rock climbers because they
Yeah,
can't
they're like
reach.
lanky. Everybody
Yeah,
that I see that's like really good at rock climbing is like super lanky but has some upper body strength.
yeah. And when you look at them, they got like the V back, you
Yeah,
know.
exactly. They've got like some like yeah, they
So they
have
got
some
they
strength.
got the big wingspan with the arms, and they got really long
Yeah, there's some people
legs.
that have really long arm length, so I can imagine that would be like really helpful as
Yeah,
well.
and then you got to be able to put your hand and your foot on the same hold, and then reach up with your other hand.
Yeah, there's people that are just naturally have a gift in not naturally or naturally have a advantage over other humans.
Absolutely, and I'm not that person. I just have the chemistry advantage.
Yeah, exactly. Well, thank you so much, Tony. I'm gonna like try to just, go through those Q&As and try to be more actively engaged while I'm doing
Okay,
it.
we'll see you tomorrow.
And yeah, I want to make it to the 10 a.m. session because I need to be better about that.
All
And I
right.
actually wanted to go through some of the stuff from chapter 9 because that one
Uh,
was kind of tricky.
9 was the valence
Not, but
bond.
not tomorrow, but maybe possibly on Thursday or Friday.
Now, also in the miscellaneous module at the bottom, there's a couple of documents
Uh-huh.
where there are line drawings of molecules. And your job is to identify functional groups in all of those drawings.
Oh, okay.
And below that document, there's the key to that document.
Okay.
So you can see the document without the key, you can give it a shot and compare it to the key. And
Great.
there are 4 pages of molecules to look at.
Okay.
So
Sounds
that's
good.
something that's always on the exam is here's a molecule, what are the functional groups?
Yeah.
You're supposed to circle them and name them.
Yeah. Okay.
All right.
All right. Sounds good. Thank you, Tony. Have a good
You betcha.
evening.
We'll catch you tomorrow.
All
Bye-bye.
right. See you. Bye.